welcome to This Explainer. Today, we're putting on our engineering hats to methodically dissect the acoustic ecosystem of the loudspeaker. We're going to reveal what I like to call its invisible architecture. You know, as listeners, we tend to obsess over the visible stuff, right? The drivers, the magnets, the cones. But as any lead acoustic and structural engineer will tell you, the environment surrounding that cone is actually doing some incredibly heavy lifting that you literally cannot see. Okay, so let's dive right into a fundamental question. Picture this. You're standing in front of a massive rig, and you feel that deep, perfectly controlled low-end thump just hit your chest. What's actually creating that? I mean, is it just the speaker cone moving back and forth pushing air, or is it something else entirely? Well, to answer this clinically, we really have to look past those visible components. And to do that, we must first establish a core concept, and that is acoustic suspension. This is a design that relies on the exact liters of air trapped inside a sealed cabinet to act as an actual mechanical compression spring. So instead of relying solely on the stiff physical suspension built into the speaker driver itself, this system uses the enclosed air's elastic cushion to provide the restoring force. It's a truly brilliant piece of invisible engineering that precisely dictates the linear movement of the cone. Here's our laboratory itinerary for today. We'll cover 1. The invisible architecture, 2. The lung's internal volume, 3. The skeleton material science, 4. Baffle engineering and resonance, and 5. The mechanical EQ filter. All right, starting with section 1, the invisible architecture, beyond the free air driver. It's actually a super common misconception that the driver all by itself generates the tone. It doesn't. If you take a high-quality speaker driver and just suspend it in free air completely outside of a cabinet, it lacks acoustic impedance. What happens is the sound waves coming from the rear of the speaker basically wrap around and instantly cancel out the sound coming from the front. The acoustic result, a remarkably thin, weak sound. So, the cabinet's primary function is to surgically isolate that rear wave, which allows the frontal sound to actually project out and reach you. Let's move on to section 2, the lungs. Internal volume, controlling excursion, and thump. This perfectly illustrates the physics of air within the enclosure. Broadly speaking, we have two main approaches. A sealed cabinet uses that internal volume of air as a direct compression spring, which creates a highly controlled, tightly regulated environment for the driver. Conversely, a ported cabinet operates as a tuned Helmholtz resonator. It uses a very specific volume of air connected to the outside world through a mathematically tuned port to physically reinforce the bass fundamentals. It effectively creates an acoustic filter that amplifies those lower frequencies. Now, take a look at the exact number shown here, 0.7. In acoustic engineering, this QTC alignment factor represents the absolute laboratory ideal for a sealed cabinet system. Hitting this number provides the best possible combination of an even frequency response and deep extended bass. If you mess with the internal volume and that number creeps up above 0.7, well, you start getting this artificial hump in the bass response, a boomy, muddy quality that completely disrupts clinical accuracy. But here's the catch. That precise sealed control comes at a really steep mechanical cost. The exponential mechanical demand on a sealed system is severe. To put it in perspective, at 25 Hz, which is deep, deep down in sub-bass territory, we are asking the sealed speaker cone to do literally 3 times the mechanical work compared to a ported alignment just to maintain the exact same acoustic output, 3 times. This is exactly why sealed systems demand significantly more amplifier headroom and massive driver excursion capabilities. All right, section 3, the skeleton, materials science, panel resonance, and cabinet coloration. So the crucial point here is comparing these two dominant materials, 13-ply Baltic birch and MDF, or medium density fiberboard. Baltic birch possesses an incredibly high stiffness to weight ratio. This cross-grained rigidity actually forces panel resonant modes upward in frequency, which results in superior transient speed and a highly defined acoustic projection. On the flip side, MDF is heavy, it's uniform, and it completely lacks a grain. That gives it extreme internal damping. It deadens unwanted resonance brilliantly, sure, but it can sometimes muddy the overall audio quality just because of how its amorphous structure absorbs acoustic energy. Now, aside from the outer shell material itself, the internal void presents its own unique set of acoustic nightmares. To combat the strongest standing wave, which typically forms by bouncing violently between the back of the speaker and the rear wall, usually peaking right around 950 Hz, engineers have to rely on precise internal damping treatments. Materials like open-cell acoustic foam are clinically applied to absorb those high-pressure reflections long before they can re-enter the cone and cause audible distortion. Moving into section 4, baffle engineering and resonance, managing the sound launchpad. This leads us to a genuinely fascinating mechanical flaw known in the industry as the oil can effect. If a wooden front baffle or rear panel isn't heavily structurally reinforced, the immense internal air pressure changes driven by the speaker cone will cause the wood to physically bulge outward and then suck back inward. It behaves literally like a flexible metal oil can. This flexing is a massive problem. It robs the speaker of its acoustic power, drastically decreases efficiency, and induces sympathetic, muddy vibrations that completely ruin the analytical precision of the sound. To counteract this violent mechanical energy, structural engineers employ some very strict decoupling tactics. This includes things like drastically increasing the baffle thickness or utilizing complex dual material construction, like physically mounting rigid aluminum plates directly onto an MDF board. It also involves mounting the drivers themselves onto isolated sub-baffles and using heavy damping gaskets to prevent direct energy transfer from the driver's frame straight into the cabinet skeleton. The ultimate goal here is to either purposefully add calculated musical life to a guitar signal or to ensure absolute clinical precision in a studio monitor without any blurring whatsoever. And finally, Section 5, the mechanical EQ filter, the unavoidable coloration. What you really should take away from all of this is that despite our absolute best engineering efforts, a loudspeaker enclosure is never, ever truly inert. Because of finite stiffness, structural mass, and those air spring physics we've been discussing, the cabinet itself functions as a massive, permanent mechanical EQ filter. The specific wood you select, the exact internal volume, the structural bracing layout, all of it drastically alters the final frequency spectrum that actually reaches your ears. The invisible architecture is actively and unavoidably coloring the sound you experience. Which brings us to this rather profound acoustic truth. The box is the instrument. As you think about the clinical physics we've dissected today, the lung-like compression of the air, the skeletal resonance of the Baltic birch, the sheer violence contained by that front baffle, I want you to ask yourself a question. The next time you sit down to critically listen to your favorite track, are you really just hearing the speaker cone, or are you truly listening to the complex, carefully engineered, invisible architecture of the box itself? Thank you for joining me on this explainer. Keep analyzing, and I'll see you next time.